Running the system bonding ground, also known as the grounding electrode conductor, outside of the conduit and connecting it to the other grounding components at the transformer introduces the potential for objectionable current. The grounding electrode conductor is designed to provide a low impedance path for fault currents. The equipment ground's primary purpose is to bond non-current carrying metal parts to the grounding system. Connecting these two separate grounding paths together creates a parallel path for fault currents. This situation can lead to excessive current flow through the equipment ground and/or grounding electrode conductor, potentially causing overheating, damage, and safety hazards. To mitigate these potential issues, it's generally recommended to run the grounding electrode conductor inside the conduit alongside the other conductors, then connect it to the grounding system at the transformer using a ground bushing. This approach ensures the grounding electrode conductor is properly protected and fault currents flow through the intended path. If the grounding electrode conductor is already installed outside the conduit, there's an alternative option. This involves isolating the equipment ground from the grounding electrode conductor and other grounding components at the transformer. This can be achieved by connecting the equipment ground to the transformer frame using an insulating bushing or barrier, while maintaining the electrical connection between the grounding electrode conductor, transformer frame, and ZER. When dealing with grounding systems, it's important to understand the roles of different conductors and components. The grounding electrode conductor connects the system's grounded conductor, typically the neutral, to a grounding electrode, such as a ground rod or metallic water pipe. This provides a path for fault current to return to the source, allowing overcurrent protective devices like circuit breakers or fuses to operate and clear the fault. The equipment grounding conductor, on the other hand, connects the non-current carrying metal parts of electrical equipment, such as enclosures and conduit, to the grounding system. This ensures that if a fault occurs and a metal part becomes energized, the fault current will flow back to the source, tripping the overcurrent protective device and preventing electric shock. Objectionable current refers to current that flows on grounding conductors but is not related to a fault. This current can be caused by a variety of factors, including unbalanced loads, inductive coupling, and improper grounding practices. Objectionable current can cause nuisance tripping of overcurrent protected devices, overheating of grounding conductors, and interference with sensitive electronic equipment. Several factors can contribute to objectionable current in grounding systems. Firstly, multiple ground paths can create parallel paths for current flow. When the grounding electrode conductor is run outside the conduit, it creates a parallel path for fault current, as mentioned earlier. This can lead to excessive current flow on the grounding electrode conductor and equipment grounding conductor. Secondly, unbalanced loads can also cause objectionable current. In a three-phase system, if the loads on each phase are not equal, current will flow on the neutral conductor. This neutral current can then flow onto the grounding system if the neutral and ground are bonded together at multiple points. Thirdly, inductive coupling between conductors can induce current in the grounding system. This is especially common in long runs of parallel conductors. Finally, improper grounding practices can also contribute to objectionable current. This includes things like using undersized grounding conductors, making improper connections, and failing to properly bond all metal parts of the electrical system. There are several steps that can be taken to minimize objectionable current in grounding systems. Firstly, ensure that the grounding electrode conductor is run inside the conduit along with the other conductors. This will help to minimize the creation of parallel paths for fault current. Secondly, balance the loads on each phase of the system. This will help to reduce the amount of current flowing on the neutral conductor. Thirdly, minimize the length of parallel conductor runs and separate them as much as possible. This will help to reduce inductive coupling. Fourthly, use properly sized grounding conductors and make sure all connections are clean and tight. This will ensure that the grounding system has a low impedance path for fault current. Fifthly, bond all metal parts of the electrical system together, including enclosures, conduit, and equipment. This will help to ensure that fault current will flow back to the source and trip the overcurrent protective device. The National Electrical Code, NEC, provides specific requirements for grounding and bonding electrical systems. These requirements are designed to minimize the risk of electric shock and fire. Some of the key NEC requirements related to grounding include Article 250, which covers grounding and bonding in general. It specifies the requirements for grounding electrodes, grounding electrode conductors, equipment grounding conductors, and bonding. NEC Section 250.4 covers general requirements for grounding and bonding. This section emphasizes the importance of creating a low impedance path for fault current to return to the source. It also specifies the requirements for grounding separately derived systems, such as generators and transformers. NEC Section 250.24 covers grounding of service-applied alternating current systems. This section specifies the requirements for grounding the neutral conductor at the service equipment. It also covers the sizing and installation of the grounding electrode conductor. NEC Section 250.66 covers the sizing of the grounding electrode conductor. This section provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. NEC Section 250.104 covers bonding of metal water piping systems and other metal parts. This section requires that metal water piping systems and other metal parts that are likely to become energized be bonded to the grounding system. NEC Section 250.118 lists acceptable types of equipment grounding conductors. This section specifies the types of conductors that are permitted to be used as equipment grounding conductors, including copper wire, aluminum wire, and rigid metal conduit. When troubleshooting objectionable current, there are several steps you can take to identify the source of the problem. Firstly, use a clamp-on ammeter to measure the current flowing on the grounding conductors. This will help you to determine if there is excessive current flowing on the grounding system. Secondly, check for multiple ground paths. Look for any places where the neutral and ground are bonded together at multiple points. Thirdly, check for unbalanced loads. Use a voltmeter to measure the voltage on each phase of the system. If the voltages are not equal, there may be an unbalanced load. Fourthly, check for inductive coupling. Look for long runs of parallel conductors. Fifthly, inspect all grounding connections to make sure they are clean and tight. If you find any loose or corroded connections, clean them and tighten them. If you are unable to resolve the problem yourself, consult with a qualified electrician. They will have the knowledge and experience to troubleshoot the problem and make the necessary repairs. Let's delve into the specifics of why running the grounding electrode conductor outside the conduit can lead to issues, and explore alternative solutions in more detail. When the grounding electrode conductor is run outside the conduit, it creates a parallel path for fault current to flow back to the source. This parallel path is less controlled and predictable compared to running the grounding electrode conductor inside the conduit. The impedance of the grounding electrode conductor run outside the conduit can be higher due to its length and exposure to the surrounding environment. This higher impedance can cause fault current to divide between the grounding electrode conductor and other available paths, such as the equipment grounding conductor. Because of the uncontrolled current division, the equipment grounding conductor might carry more current than it is designed for. This can lead to overheating of the conductor, potentially damaging the insulation and creating a fire hazard. Furthermore, the increased current flow in the equipment grounding conductor can create voltage drops along its length. This voltage drop can raise the potential of the metal parts connected to the equipment grounding conductor relative to ground, increasing the risk of electric shock. Running the grounding electrode conductor inside the conduit provides a more controlled and lower impedance path for fault current. The conduit acts as a shield, reducing inductive coupling and minimizing the potential for fault current to flow on unintended paths. The lower impedance of the grounding electrode conductor inside the conduit ensures that most of the fault current flows through it, minimizing the current flow in the equipment grounding conductor. If running the grounding electrode conductor inside the conduit is not feasible, isolating the equipment ground from the grounding electrode conductor and the other grounding components at the transformer is a viable alternative. This involves connecting the equipment ground to the transformer frame using an insulating bushing or barrier. This prevents fault current from flowing directly from the equipment grounding conductor to the grounding electrode conductor. Instead, fault current flows from the equipment grounding conductor to the transformer frame, and then through the grounding electrode conductor to ground. Maintaining the electrical connection between the grounding electrode conductor transformer frame and so the neutral point of the transformer is crucial for ensuring a low impedance path for fault current. This connection provides a direct path for fault current to return to the source, allowing overcurrent protective devices to operate and clear the fault. When isolating the equipment ground, it's important to ensure that the insulating bushing or barrier is properly rated for the voltage and current levels present in the system. The insulating material should be able to withstand the potential voltage difference between the equipment grounding conductor and the transformer frame without breaking down. Furthermore, the insulating bushing or barrier should be installed in a way that prevents moisture or contaminants from entering the connection, as this can reduce its insulating properties. In addition to the grounding electrode conductor and equipment grounding conductor, other grounding and bonding components play an important role in ensuring electrical safety. These components include bonding jumpers, which are used to connect metal parts together to create a continuous grounding path. Bonding jumpers are typically used to bond metal conduit, enclosures, and other metal parts to the equipment grounding conductor. Grounding electrodes, such as ground rods and metallic water pipes, provide a connection to the earth. This connection helps to stabilize the voltage of the electrical system and provides a path for fault current to dissipate into the earth. Ground fault circuit interrupters, GFCIs, are devices that detect ground faults and interrupt the circuit. GFCIs are typically used in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Arc fault circuit interrupters, FSIs, are devices that detect arc faults and interrupt the circuit. Arc faults are dangerous electrical conditions that can cause fires. FSIs are typically used in bedrooms and other areas where there is a high risk of fire. Proper grounding and bonding are essential for ensuring electrical safety. By following the NEC requirements and implementing best practices, you can minimize the risk of electric shock, fire, and equipment damage. Remember to consult with a qualified electrician if you have any questions or concerns about grounding and bonding. They can help you to design and install a grounding system that meets the specific needs of your application. Furthermore, regular inspection and maintenance of the grounding system is important to ensure that it remains effective over time. This includes checking for loose connections, corrosion, and damage to grounding conductors and components. Any issues identified during inspection should be addressed promptly to prevent potential safety hazards. Firstly, consider the system's voltage. Secondly, examine the available fault current. Thirdly, evaluate the equipment grounding conductor size. Fourthly, inspect the grounding electrode conductor size. Fifthly, confirm the bonding connections. Sixthly, verify the grounding electrode system. Seventhly, assess the presence of objectionable current. Eighthly, review the overcurrent protection. Ninthly, consider the environmental conditions. Tenthly, consult with a qualified electrician.